All right, guys, so we're going to study the antiderivative in this section. We're switching it up quite a bit from the first half of the course when we studied differential calculus. Now we're transitioning into integral calculus. And so the thing to remember as we move forward with what I'm going to show you is that a derivative is a transformation. It takes a function and it transforms it into another function. The antiderivative, being the opposite of the derivative, is going to allow us now to move backwards into that original function. So we've got a small example up here, y equals x squared. So if I want dy dx, we all know by now that's going to be 2x. So nothing crazy there. But now, off to the side here, I'm going to write this dy dx equals 2x. And we're going to work backwards now using the antiderivative to come up with this thing right here. So a couple of weeks ago, we talked about how you can treat the dy and the dx independently. And so I'm going to take this dx and I'm going to multiply it to the other side to where I have dy equals 2x dx. And then I'm going to take the antiderivative of both sides. Most of the time you'll hear me say we're going to integrate both sides. So this symbol in red, that's the integral symbol. And so it's going to tell us we want to find the antiderivative. Now, on the left, it's interesting because this is the antiderivative symbol, but that D stands for the derivative, right? The derivative of y. So these two things operating on each other essentially cancel each other out. So on the left, all we have is this y that's left over. Now on the right-hand side, we're going to have to actually take the antiderivative or integrate this thing here. And to do so, the process, because of what it is going to be the exact opposite of finding the derivative. So to find the derivative, our rules were pretty simple. The first thing you would do is you would multiply the exponent down, and the second thing is you would subtract 1, which means the rules for the antiderivative are going to be the complete opposite. The first thing we're going to do is add 1 to the exponent, and the second step then is going to be to divide. So our current exponent here is a 1. I'm going to add 1 to it, so 1 plus 1 is 2, and I'm going to divide by 2. So let me write this out. This 2 that I'm writing right here, that's this guy here. I need to divide by 2 because I added 1 to the exponent. So that 2 right there is me dividing right here as well. So when I simplify now, that just gives me my x squared. Now, there's a little bit of a catch. The catch is, if my original problem was something like this where we're adding 7, then this wouldn't be any difference because the derivative of a constant would go to 0. So for us to truly get the antiderivative, we have to be a little bit careful. Every time you take an integral like we have, we're going to need to remember to put a plus c at the end for our final answer. That constant is needed because, again, we don't know if it was there to start. If it wasn't, then c would just be 0 anyway. But if it was 7, then we're taking that into consideration. So anytime we integrate like we have, we're going to have this plus c tacked onto our final answer. So let me summarize the procedure of finding the integral like we have. So in a general form, if we have the integral of x raised to the n dx, this is going to equal 1 over n plus 1 times x raised to the n plus 1 plus c. You can see I added 1, I divided by it, and then I tacked on the plus c there at the end as well. So this will be a really important form to remember moving forward now as we look at some more complicated problems. Now, before we do look at some more complicated problems, I want to outline 2 properties for you real quick. The first property says that if we have a constant multiplied by a function in an integral, that we can pull this constant out, much like we would have for a limit. The second property, before we start our examples, would be if we have a sum or difference of functions, we can split this up into two separate integrals. We could say the integral of f of x dx plus or minus the integral of g of x dx. Okay? Lastly, notice how every single time I write an integral symbol, I've got this dx. Every time I write it, I've got the dx. Every time the dx. And down here, a single integral, a single dx. Every time you write an integral symbol, though, you have to have the dx. That dx is going to tell us what we're integrating with respect to. It won't always be an x. It could be a theta, it could be a t, it can be anything. But no matter what, every time you write an integral symbol, you have to have this d whatever tacked on at the end.